So trying to figure out the optimum drug dose that you want to give to maybe, like I said, inhibit some enzyme to inhibit Abl kinase when it's turned on continuously and you don't want to have leukemia anymore. So ligand binds to 2 different receptors. How do I pick the concentration that inhibits what I want to, but doesn't have all these negative effects on other types of kinases? And again, this is the difference in KD lets us make that decision. Okay? So here's sort of a faux example. You have a drug that binds to a target receptor A with 1 nanomolar affinity or 1 nanomolar dissociation constant. And the drug can also bind to receptor B with 10 micromolar affinity. What concentration should we use to deliver the drug safely? Okay? So why don't you take a second and talk to someone next to you about how you think you would go about this without even, I mean, you can come up with an answer if you want, but how do you begin to approach it? I should hear conversation.
For the and then see like because if you have the it would be 50% saturated target drug and essentially not. So nano is ignited I guess it just depends on how much of an issue you have with finding something.
Yeah, it's just
I think it's also complicated. There must be like a maximum permanent point where it's
that makes sense because that's what you do with your So what would that be for the other one? We're solving for
Did you listen to the thing, or did someone just tell you about it?
I watched the lecture.
Yes.
And I asked very
You can have a bite of soup. Yes, you. But how would you offer, like,
colloquially a bite is an amount. What would you like?
yeah, like a small amount of this? Yeah. That's it. It's going on the final survey. I need the official data. No anecdotal evidence. I need it.
This is my last bite of soup.
You can say that because it's like the last. It's the little amount. Like, yeah, it does. All right, so who wants to tell me what drug dose they settled on or how they thought about this problem? How do you go about deciding? Do it. Someone answer. Yes.
So I mainly just want to stay below 0.1 maybe of the receptor B, then I should be good. Then like be essentially fully bound to target receptor A.
Okay, so that approach that Lauren said was trying to stay at a ligand concentration that was less than 0.1 of the KD of receptor B, so that you can keep like less than 9% of it bound up. And then, so that's one way to work. Think about it. Any other, how'd you like start to decide what you think you want? So I mean, again, looking at sort of fractional saturation is what you want to do. You want receptor A to have most of it bound, and you want to have receptor B, sort of most of it not be bound. And so you're sort of looking for a concentration that will be in between these two is where it's going to work. Okay? And you can do, sort of the math for it In the book, it talks about using 0.1 micromolar or 10 to the negative 7th molar, and what you'll see is that for your target then, if you were to plug these numbers in, you'll get about 0.99 or 99% of receptor A will be bound, but only 1% of receptor B will be bound. So here is another example problem that you should take a minute and solve with some people around you, okay? Drug UM1 with molecular weight 540 Daltons, which is grams per mole, binds to enzyme BLU2 with a dissociation constant of 0.1 nanomolar. What mass of UM1 needs to be administered to a patient with a blood volume of 5.5 liters so that BLU2 will be at least 90% inhibited, okay? I will go ahead and tell you right now that yes, you can use 90 exactly to do this, but we learned a really easy, quick jump ahead that gives you 91. You're free to use it. One of the questions